So in this video, we're going to be exploring the properties of light, and I should be more specific, or more general, I should say, properties of what we call electromagnetic radiation. And this is what we generally think of as light, like the light that we see all around us, but it's not just that light. So electromagnetic radiation comes in all sorts of varieties, depending on its properties. So things like, so we'll make a little list here. So we have visible light, but things like microwave radiation, microwaves, those are another form of electromagnetic radiation. We also have things like infrared light. I in particular use this kind of light in my research, and I use it to study molecules. We also have things like X-rays. You know, if you use an X-ray machine at a hospital or something, that uses also a different form of light. Or things like UV light, ultraviolet, that we try and avoid so that we don't age our skin or get sunburns. And there are a few other ones that I haven't listed here. But all of these are different types of the same thing. They're all what we call electromagnetic radiation. Now, electromagnetic radiation, it's a mouthful, we can think of it as energy that propagates in waves. So what do I mean by that? I mean, we call it electromagnetic radiation because it's composed of both an electric field and a magnetic field, and they perpetuate themselves. So the electric field grows and decreases just like the magnetic field does, and it behaves sort of in this way. They propagate, the electric field goes up and down, magnetic field goes left and right, relatively speaking, compared to the direction of propagation. So, how do we understand this light, and how do we make sense out of it? Well, there are some properties of electromagnetic radiation that tell us what kind of light we have and what sort of energy it has. So, one property of electromagnetic radiation or light is that it has a constant speed. And this is the speed of light that we call c. We give it the symbol c. And it is equal to 2.998, and we can add some more digits, but times 10 to the 8th meters per second. And this is the fastest thing we know of in the universe. There's nothing that can move faster than the speed of light. So you're probably familiar with that idea. And so all light of all types moves at this speed. Visible light, microwaves, infrared, X-ray, UV, any kind of light you name. So light has this constant speed, and it's very fast. Light has no mass. That's another thing that's part of it. It's basically sort of pure energy in the form of a wave. And since it's a wave, we can characterize it by some properties of waves. So one is what we call a wavelength. And that is if we sort of draw the wave, now just looking at, say, just the electric field, going up and down here, we have a distance from the top of the wave to the next top of the wave as it's moving through space. And the distance between that is called the wavelength. And electromagnetic radiation can have all sorts of different kinds of wavelength. So we have wavelengths for visible light that are very short. So something like 600 nanometers is on the edge of the visible wavelength. This will be, a sort of reddish color. And so just remembering our prefixes here, this is 600 times 10 to the minus 9 meters. So quite small, a very small distance in terms of the wavelength. But wavelengths for so this would be visible light. But wavelengths for electromagnetic radiation can be very large as well. So you can have wavelengths on the order of meters, something like, 1 meter can also be a perfectly valid wavelength. This would be something in the radio wave, which is another type of electromagnetic radiation that I didn't include on my list before. So, if you enjoy listening to the radio in your car, you can think electromagnetic radiation, because that's what's sending the signal, and that's what's being picked up by your antenna in your car. So different wavelengths will have different what we call frequencies as well. So, a shorter wavelength like this one, in comparing A and B here, this will have since light is moving at a consistent speed, the shorter the wavelength, the higher the frequency. So let's first of all name. I forgot to name this. This symbol here is called lambda. This is a Greek letter, and this is the symbol we use for wavelength. And the other thing we often talk about as well is what we call frequency, and that's how many cycles per second, or how many times the wave waves in every second. So if you sort of pick a point, say this point here, and our wave is coming this way, how many times does a peak come through every second? Right, so as this moves to the right, we pick a point here. Every time a peak comes through, that would be one cycle. And how many times does that happen per second? So we give this the symbol nu. It looks like a V, but it's not a V. It's the Greek letter nu. And there's a relationship between nu and lambda, frequency, wavelength, and the speed of light, which is a pretty simple one, actually. The speed of light is equal to the wavelength times the frequency. And this is actually true for all waves, not just light. But with light, that speed is constant. But if you think of ocean waves or sound waves, they also have this relationship that the speed of the wave is related to the wavelength of the wave times the frequency of the wave. Just for light, that speed is a consistent value. One other thing we can think about as well in terms of light is sort of how bright it is, which is represented by the amplitude, which is basically just how tall is the wave. So the larger the electric field is, the brighter that light will be. And so that is another property of the wave that we can consider. So these are equations we can use to describe light and tell us more about the different kinds of electromagnetic radiation. I use light, I mean any kind of light, any kind of electromagnetic radiation. So I'm just going to pull up one more figure here that shows, there it is. Give myself some space here, see how well this shows up. All right, gotta undo the full screen, blow this up. And this just to make sure I talk about all the different wavelengths of light. Now that we talked about wavelengths and frequencies, we'll use this figure here to look at sort of the different types of electromagnetic radiation you can have. So going from on the right-hand side, we have the longest wavelengths. So the wavelengths are down on the bottom here. So these are like 10 to the fourth, 10 to the second. These are like 1,000, 10,000 meters in terms of wavelength, which is like really, really big. These are radio waves. And as we get shorter, we get microwaves here in the 10 to the minus 2 meter range. Then into the infrared, my favorite part of the spectrum, here in the 10 to the minus 4 to 10 to the minus 6. And then we get our little bit, the light we can see is just this little band here. That's represented by the colors we have here. And then beyond that, we have then ultraviolet, 10 to the minus 8, X-ray, 10 to the minus 10, and then we get into gamma rays, which are really, really high energy. And so the energy of the light, how much energy it carries, increases to the left on this figure. But the wavelength increases to the right, so that's why it's plotted the way it is. So things like radio waves have very low energy on this side. And these are things we use in like cell phone towers, use radio waves, our radios in our cars and things like that. Wi-Fi uses radio waves as well. And then the really high energy light is on this side, and these are very damaging. So things like an X-ray, you're only exposed to it a very short amount of time because it can cause a lot of damage to the molecules in your body. So this is a little bit of an introduction to light, and we can calculate, using this, again, I'm going to write this equation again, C equals lambda nu. If we know C is a constant, it's at 2.99 times 10 to the 8th meters per second. So that means if we know a wavelength or a frequency, we can find the other one. So we can find the relationship between these two things. So that's our crash course. There's a lot more to know about light, but this is a crash course in properties of light. And in the next video, we're going to start looking into some of the measurements done using light that scientists were doing in the early 1900s, late 1800s, that helped them realize that our picture of the universe was not complete, and that we needed there were some things we didn't know about what was happening with things on an atomic and molecular level.